Okay, we are picking up where we left off in the 2.1 notes. In the previous video, we had discussed percentiles, measures of location, and then when you transform data sets, either by adding or subtracting a number, or by multiplying or dividing all the observations by a number, how that affects measures of center, spread, and the shape of the distribution. Okay, we're going to discuss another measure of location today. Instead of a percentile, we're going to look at something called a z-score. Okay, and a lot of times you're going to hear the term standardizing, and that is referencing what we call a z-score. And so we're going to revisit this idea of where it mentions that Jenny scored an 86 on her test. Here we have the stem and leaf plot again. Okay, I'm just going to highlight her score right there would be Jenny's score. And we had answered this question, what her percentile was on the previous notes here. You can see that you are given some computer output. It's important that you can look at this output and find what it is that you're looking for here. This is short for trimmed mean. It's not something that we use in AP statistics. It's beyond the scope of this course. You won't have to worry about that. This is something that we'll talk about at a later date. But what we're really interested in here is we want to be able to describe Jenny's location, where she falls in the distribution of her class's test scores, but we want to do this by telling how many standard deviations above or below the mean her score is. Okay, so this is all about how many standard deviations. So up above in this output, I'm going to circle for Jenny's entire class, the standard deviation of this set of data is 6.07. Now remember what that means. That means typically if you were to randomly select one score at random from this class, in general, the scores are falling 6.07 standard deviations from the mean. Okay? That's typically how far off they're 6.07% from the mean. Okay. All right, and here's the mean of Jenny's class. 80% was the average. Okay. So if we're looking to figure out how many standard deviations is Jenny's score, okay, from the mean of 80, this is the formula that we use to calculate a z-score. Okay. Now I'm going to write this formula down. We can discuss what these variables represent. This stands for the individual observation. In this case, that would be Jenny's score. This is the mean of the entire data set, and this is the standard deviation of the entire data set. So for this problem, we would plug 86 in for the x, that's Jenny's score, minus 80, that's the mean, and divide by the standard deviation, and we would roughly get 0.99. So that means that her score, it's almost one standard deviation, but it's 0.99 standard deviations above the mean, okay? Because she had a positive z-score, it means Jenny is above the mean. If you get a z-score that's negative, then you're that many standard deviations below the mean. So if you look at this, see how there was a difference of like 6%, and then look at what the standard deviation was, a little bit over 6%. That's where we're getting, she was almost one of these standard deviations, 0.99, almost one of them away from the mean. Okay, so standardizing is when you convert an original value into standard deviation units. Okay, the formula, this is something you'll want to commit to memory, to calculate a z-score is x minus mu divided by sigma, which is the observed value minus the mean divided by the standard deviation. Okay, something worth noting is the z-scores are not measured in the same unit as the variable. So when you say 0.99, that is 0.99 standard deviations, not 0.99%, because that's what these data pieces represent. Okay, it's in standard deviations from the mean. Okay, one other thing just worth mentioning is that z-scores, when you talk about transforming, adding, subtracting, multiplying, dividing by an entire data set, z-scores are unaffected by transformations, okay? So adding, subtracting, multiplying, and dividing an entire data set, it won't affect the z-score. Okay, so let's go ahead and take a look at example 7. It says find the standardized z-score for each of the following students in Jenny's class. So I'm going to make sure we can still see this was the standard deviation, this is the mean here. Okay, we want to interpret each value in context. So here we have Katie, she scored a 93. I'm going to use our z-score formula right here. I'm going to take Katie's score of 93 minus the mean of 80. I'm going to divide that by the standard deviation of 6.07, and I'm going to get 2.14. Okay, this means that Katie's score is 2.14 standard deviations above the mean. Okay. You always want to say whether that piece of data is above or below the mean, and that's dictated by whether your z-score is positive or negative. Okay. She scored even better than Jenny, so she was even more standard deviations above the mean than what Jenny was. Okay. Then we have poor Norman here. Norman got a 72, so we're going to convert his score into a z-score, and we get negative 1.32. So we're going to say Norman's score is 1.32. I'm not making it negative here. I'm going to say 1.32 standard deviations, and then I'm going to choose the word below because it was negative, below the mean score. Okay? All right, let's take a look at example 8. Here, this is talking about Mr. Navard's statistics class has just completed the first 3 steps of where do I stand. The figure below shows a dot plot of the class's height distribution along with the summary statistics from the computer output. Okay, I'm going to go ahead and highlight for the class. Here's the class average height, 67 inches. Here's the class spread, the standard deviation, typically how far. If you were to pick someone at random, they would typically be about 4.29 inches from the mean height of 67. Okay, first question. Lynette is a student in the class. She is 65 inches tall. Find and interpret her z-score. Okay, so this is number 1 here. Okay, we're going to change Lynette's height into a z-score by using this formula. Her height, it said, was 65 inches. We're going to take her height minus the mean divided by the standard deviation. We get negative 0.47. We're going to say that Lynette's height is 0.47 standard deviations below the mean class height. Okay, that means she's on the shorter side compared to others. Okay, all right, number 2. Another student in the class, Brent, he's 74 inches tall. Okay, how tall is Brent compared with the rest of the class? Give appropriate numerical evidence to support that answer. Okay, this is just really asking you to do the same thing we did in number 1 with Lynette. We want to change his height into a z-score so that we can compare if he's above the mean, if he's below the mean, and by how much. Okay, because obviously you can see his height, see that it's above the mean, so we know we're going to get a positive z-score. Okay, but we're going to say Brent's height is 1.63 standard deviations above the mean class height. Okay, let's look at number 3. Number 3 says Brent is a member of the school's basketball team. Now, this is interesting. The mean height of the players on the team is 76. Brent's height translates to a z-score of negative 0.85 in the team's height distribution. the question, what is the standard deviation of the team members' heights? Okay, so what I like to do when I'm reading through problems like this, and you can see I kind of highlighted the important pieces of information, I'm going to write down off to the side the mean of the height of the players on the team was 76 inches. Okay, the other piece of information they gave us is it looks like he's a little on the short side when it comes to being compared to his team members. He's falling 0.85 standard deviations below the mean, but this question's asking us to find the standard deviation. Okay, so let's think about this z-score formula here. Okay, it has standard deviation in the formula. So if we can plug numbers in for these three variables here, we should be able to use algebra to work backwards, okay? His z-score when he's compared to the team is negative 0.85. His height, I'm coming back up to number 2 to get this, is 74. Team's average height is 76, and I don't know sigma, the team's standard deviation. That's what I'm trying to find. Okay, so I'm just going to use algebra here. We're going to multiply both sides by sigma. Okay, I'm going to get a negative 2 on this side when I subtract 76 from 74, and then I divide by negative 0.85, and I get that the team's standard deviation is roughly 2.35 inches. Okay. Okay, let's take a look at this example called Too Cool at the Cabin. Okay, and we're going to go back and revisit this idea of how does the shape and the center and the spread get affected when you transform data. It says during the winter months, the temperatures at the Starnes, Colorado cabin can stay well below freezing. Okay, so it's falling under 32 degrees Fahrenheit or 0 degrees Celsius. It can be like that for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She also buys a digital thermometer that records the indoor temperature each night at midnight. Unfortunately, the thermometer is programmed to measure the temperature in degrees Celsius. Okay? So this dot plot here is recording what the temperature is at midnight. It did the midnight temperatures for a 30-day period. So there are 30 dots in this dot plot, but it's measuring the temperature in Celsius, and we are interested in figuring out what it is in Fahrenheit. Okay, you can see here we have some computer output. Okay, and then they give you the formula for how to convert from Celsius to Fahrenheit. Problem number 1 says, or part A rather, says find the average temperature in degrees Fahrenheit. Okay, now if you look at the computer output, we have the average temperature, but the average temperature of 8.43 is 8.43 degrees Celsius. Okay, now what we're not going to have to do is we don't have to take each of these individual dots, convert each one into Fahrenheit to create a totally different dot plot. That's way too time consuming. That is why we learn how transformations can affect measures of center, measures of spread, and the shape. Okay, so we had learned in the previous video that the mean, since that's a measure of center, it is absolutely influenced by both addition and subtraction, as well as multiplication and division. Now, why is that important to note that here? And I'm going to go ahead and put A here for our first part here. Well, if the average Celsius temperature is 8.43, and I want to convert to degrees Fahrenheit, if I look at what's happening, look at the math that's happening in the formula, I'm multiplying by 9/5. Well, the new mean Fahrenheit temperature, it would be influenced by the multiplication. And then I'm adding 32. Oh, measures of center, those are also influenced by addition. So I'm basically just going to take this formula, and in the spot for the C, for degrees Celsius, I'm going to substitute what the mean Celsius temperature is, and I'm going to multiply that mean Celsius temperature by 9/5, and then I'm going to add 32 to it, and I'm going to get 47.174 degrees Fahrenheit. Okay. The question is, does the thermostat setting seem accurate? Now remember up here, she set it at 50 degrees Fahrenheit, but the readings are coming out on a 30-day period on an average of 47.174 degrees Fahrenheit. So we're going to say, you know what, it doesn't seem very accurate. Okay, it's supposed to be 50 degrees Fahrenheit, and the average over 30 days is 47 degrees Fahrenheit. Okay, like it'd be okay if one night maybe it measured 47 degrees Fahrenheit, but when you're doing an average of 30, that the average is 47, kind of feels like maybe that thermostat isn't quite working correctly. Okay. All right, let's move on to part B, and here's where we're going to have to be a little bit careful. Now it says, calculate the standard deviation of the temperature readings. Again, they want us to do this in degrees Fahrenheit. So let's go back up to our computer output. I'm going to circle the standard deviation, but keep in mind the 2.27 is in degrees Celsius. So we're going to need to convert to Fahrenheit. However, measures of spread are not influenced by any transformations involving addition or subtraction. They are only influenced by multiplication and division only, okay? So when you look at the formula, if we're going to convert the standard deviation of 2.27 into what the standard deviation would be from Celsius into Fahrenheit, the only thing that's going to be influenced in this formula is that we're multiplying that standard deviation by 9/5. This whole adding 32 is not going to impact it at all. So I'm not putting plus 32 at the end there. I'm just going to fill in the standard deviation of 2.27. Okay, that's going to give me a standard deviation in degrees Fahrenheit of roughly 4.086. Okay, it did ask us to interpret this in context, so we're going to say, there's that word typical that we like to use here. The typical distance of temperature readings, okay, this is my using good context here, from the mean is about 4 degrees Fahrenheit, okay, which is an awful lot for it to fluctuate by, okay? When you set your thermostat at 50 degrees Fahrenheit, you know, maybe if it's off a degree or half a degree, fine. 4 degrees, that seems like a lot, okay? Part C, the 93rd percentile of the temperature readings was 12 degrees Celsius. That's not something that we have up here in our computer output, but they're telling you that this is where the 93rd percentile falls. They want us to convert and figure out what the 93rd percentile would be in degrees Fahrenheit, okay? Now, we're using this formula. You just have to ask yourself, what is a percentile? Well, a percentile is a measure of location. Okay, and what we know is all measures of center and all measures of location, including percentiles, they are affected by addition and subtraction and multiplication and division. Okay, so that means if I'm going to change that into the 12 degrees Celsius into what the 93rd percentile would be in Fahrenheit, I'm going to be interested in both multiplying it by 9/5 and adding the 32. Okay, and that would give me an answer of the new 93rd percentile is 53.6 degrees Fahrenheit. Okay. Okay, just a couple things to wrap up this section here. Density curves are typically when we draw a curve over top of our distribution, dot plot, histogram. The most important aspect you want to keep in mind with this is the area underneath that curve is always 1, meaning 100% of the data is supposed to kind of be located underneath there. It's also referred to as the proportion of all the observations. They're supposed to fall in that interval. Okay. Something else I'll just have you highlight here. When you look at these two density curves, and notice this one is symmetrical, this one is skewed to the right. When it's symmetrical, your mean and median are generally right in line with each other. When it's skewed, and this is the part I want you to get here, then the mean is pulled away from the median in the direction of the long tail. So see how the tail is over here to the right? That means your mean is going to be greater than your median. It's going to be pulled in that direction there. Okay, finally, on the back page, there is really just a summary down here at the bottom, a nice summary of giving you all these different types of variability. The last two are measures of center. It lists the formula for how you would calculate those things along with the variables. Gives you kind of what the pro or con might be of some of those. And then this is a really good summary. How that particular thing is affected by addition or subtraction, and how it is affected by multiplication or division. Okay, something worth noting, z-scores are not affected at all by transformations. Okay. All right, let's come back up here to the top here. Okay, we're going to fill in, sometimes researchers change units. They change from minutes to hours, feet to meters. Here's how measures of variability are affected when we change units. If you are adding or subtracting a constant to every value in the data set, the distance between the values does not change. As a result, measures of spread stay the same. However, if you multiply or divide every value by a constant, then this does in fact change the measure of spread. And we're going to talk here today about how it has an even greater effect on the variance. Okay, so let's just fill in this chart and then we'll bring this to a close here. Let's say that we have a data set. We're going to call it A. We don't know what each of the individual numbers are. We only sort of have this computer output to go by. We know these things about data set A. And let's say that you were asked to add 10 to every single value in data set A. We want to write down here, how do these measures of spread and these measures of center change? Okay, I'm just going to highlight some things here. These are measures of center. These things here are measures of spread. Okay, so if you are adding, that is when your measures of spread stay the same. So if 9 was the range for the original set of data, 9 will still be the range after you add 10. So I'm not going to make any changes to any of these. However, we know measures of center, like mean and median, those should be affected. So we should add 10 to the mean. We should add 10 to the median. Okay, here's where it gets a little bit tricky. Now we're going to talk about what if you were to multiply every number by 3. Okay, well, we know measures of center are going to be affected by that. Remember, you're going back up to the original set and multiplying that original center by 3, so 33. And this would be, 33. This would be 27. Okay, now I'm going to hold off on variance just for a second. We know measures of spread, those are affected when you multiply or divide. Okay, so each of these three things are going to then have this as your new measure of spread. Okay, now here's the part though that you have to be very careful. Standard deviation, when you square the standard deviation, you get the variance. Okay, that's why this was saying there's an even greater effect on the variance. Okay, so you don't just multiply the variance by 3. You have to multiply the variance by 3 squared. Okay, let's do that. Let's look at the answer and see if this makes sense. If I were to multiply 4 by 9, then I'm going to get 36 here. Now look at what my new standard deviation was. It was 6. Look at what the new variance is. Guess what? If you were to square the 6, you get 36. So this is the only difference with measures of spread. If it's the variance, the number you're multiplying every piece of data by, that gets squared and then multiplied by your variance, okay? All right, these problems down here should be problems that you can now go ahead and try that kind of go with the problem